I wanted to start off sort of taking a step back and reflecting on something that might even be useful tomorrow, which is talking about starting from fundamental principles. And one of the questions, now that we've got two, one of the questions is how do you decide which principle to use when attacking a problem? You can, because so use them both as possible because they're always valid. However, it's the case that they won't necessarily both be useful. You won't necessarily be able to get what you're asked for out of one principle where you could with the other. So what I want to talk about for a minute is called heuristics. Do you know what heuristics are? A heuristic is a kind of a guideline or a rule of thumb for figuring out how to attack a problem. It's not a prescription. It's not always right, but it gives you a way to think about things. So first, I'm going to write the principles we have in this way. So we have the momentum principle in the update form. Final momentum is initial momentum now plus F net delta t. We've also written the momentum principle in an instantaneous form of dp dt equals F net. And we have the energy principle, at least covered on the test, that forms with work and energy. So we have this basically a very similar update form. Final energy of a system is initial energy of a system plus work, which I'm going to write as the sum of all the F dot delta R's. That's, of course, Fx delta x plus Fy delta y plus Fz delta z. And actually, let's make this one red also. So notice that they're all always valid. Any of these equations is always true no matter what you choose as a system and what you choose as a situation. But note that this form of the momentum principle has a delta t in it. This means that implicitly, at least, there are two different times. There's some kind of time advancing. You've got two times here. So there's some T1 and some T2. In the energy principle, does time show up? It doesn't, does it? Now, time may pass because we're always talking about a system in some state and then some other state, and presumably some time elapsed in getting there. But that's not involved here. What we've got really two positions, two locations, R1 or R2, or maybe there are two separations. Anyway, we've got some distance changes here. In this one, do we even have two anythings? This is instantaneous, isn't it? This is at this instant. So chances are that just looking at a problem, now there's some other differences too, of course. These are vectors. Energy is a scalar. Even this thing with vectors in it turns out to be a scalar when you evaluate it. So you can think about a problem that's posed to you even without actually looking for what's being asked for. If you're given two times, that suggests that you might look to see if you could apply the momentum principle. If you're given two positions, locations, separations, that sounds more like the energy principle. If you're asked for an answer that's a vector, you're probably not going to get it out of the energy principle. If you're asked for a speed, maybe you can. So there are various. So these are kind of heuristics. One key thing is to draw a diagram, and if you have a diagram with two different states, then. And then I guess for completeness, I should say that we've worked some problems that don't use any fundamental principle because they're really about the nature of matter, like what's the distance, the length of an interatomic bond, or what's the stiffness of an interatomic spring or something like that. That's really just sort of analyzing matter, not necessarily using any principles. So suppose that we have, here's a problem. We have Tarzan swinging from a vine. Here's Tarzan. Here's the vine. Or actually, Tarzan's swinging from a bungee cord. How about that? Tarzan and a bungee cord. Okay. So suppose you have a problem that says, here's the ground. Tarzan is at some height 1 off the ground. He's got some speed, v1. A little bit later, he's at some height h2 off the ground, and it asks you something about that. So which one of these principles, or none, which of these things, including none, do you think you'd actually, would you decide to try to solve? I'm not really telling you what you're trying to find out, but look at what's given here. Yeah. Well, let's answer it. Answer it. Think about it. Maybe, yeah, they're numbers. Okay, there's numbers. You want numbers? 3 meters, 2 meters, 10 meters per second. That's pretty fast. Speed, how fast is he going? But it kind of doesn't matter. Okay, so the answers are 1, 2, 3, or no principle. Yeah, Tarzan's mass. I mean, what I'm trying to get you to do is look at the problem without actually trying to plug in numbers to an equation and just think, how would I probably approach it? So how would I probably approach it? What you'll find as you get more expert in solving these problems is that what you're asked for often doesn't matter. That's not the first thing you look at. What you look at is how can I analyze the situation, and I get through it and, oh yeah, by the way, what did they ask me for? Yeah, I can calculate that. I'm asking what you're going to strive first. Okay, so you can, it's a heuristic. I'm not promising you that it's going to give you the answer you need. All right, let's see. A quarter for this form of the momentum principle, about 15% for that form of the momentum principle, and about 60% for the energy principle. So let's just look at these heuristics and see what we've got here. So this one says we need 2 times. We need to be given implicitly 2 times. Are there times given here? We had some heights off the ground. We had some speeds. We've got a mass. Do we have times? That's a problem. Yeah. So we're not, what's delta T here? We don't know. Now, could you write a computer program to do this if you knew the force exerted by the bungee cord, but maybe that's changing. So, do we have two different positions? Yeah, we've got, yeah, we're that high and we're that high. So, is there something in the surroundings that might be doing work on Tarzan? Well, that's not an object, is it? The Earth. The vine. Does the vine actually? Well, it might do some work if it's stretching. Yes, the vine and yeah. So we have some energy things here. Okay. So admittedly, the details of whether this is going to work out or not uh, have to do with exactly what you're given, what you know, and whatnot. But two positions might suggest that you would like to look more carefully at energy. Okay, suppose we have Tarzan. And yes, there's some things you need to know. So if you don't know. So here's Tarzan. We've got a speed here. The vine has some length L. And we want to know the tension in the vine. Okay? So which one are you going to choose to think about first? How big is the force? It's not a vine, it's a bungee cord. How big is the force exerted by the bungee cord on Tarzan? Okay, so most people say we want to use dp dt equals F net. And what's sort of the key that makes you think this might be useful? It's at one instant, isn't it? So we don't have two times, we don't have two locations. We've got one instant. We're saying at this instant. So maybe we want to use the instantaneous form of the momentum principle. So we look to see if we've got the information we need to actually work that out. But so this is how to start, right? So yeah. Okay, so let's see. Tarzan Tarzan's speed at the velocity at this instant is that, and we know the stiffness of the bungee cord, and we know how long it is at this time, and what is Tarzan's velocity 0.5 seconds later. Okay, so maybe do we have to do this with clickers? Sure, we'll do it with clickers. All right, clickers. Okay, that definitely looks like P final is P initial plus F net delta T, doesn't it? Because you've got a delta T, and there's some things that suggest you could calculate an F net. And okay, all right. So it's not. It's all Tarzan. Let's see one more. So here's Tarzan, and let's see, the vine started out having some length, but now it's stretched a little bit, so it's got some new length L2 at this instant. And we know Tarzan's velocity. And we know, so we have a description of the vine. We know bungee cord. We know its characteristics. What's Young's modulus for the bungee cord? Well, we know what the vine, the bungee cord looked like, dimensions, and we know how long it was when we started, and we know how much it's stretched. Maybe this has more than one step, huh? Okay, so what do we need for Young's modulus? So we need a force over area, delta L over L. Okay, that will be on the formula sheet, but good. So we know how long, we know delta L, we know the original length, we know the area. We do need the force. But we actually were going to use this to figure out the force in a previous problem, right? So we decided we could use that to get a tension force. So if we did that, then we can just put it into Young's modulus. And now this isn't a fundamental principle. This is just stuff about matter. But it turns out we might have needed to use a fundamental principle. So try thinking about it that way. If you have, use as a guideline, if we've got 2 times, maybe we're going to need to do a momentum update. If it's only 1 instant, well, maybe that's the instantaneous momentum principle. If there's some changing position, maybe it's the energy principle. And it's not a guarantee, it's a heuristic, but it gives you a place to start. And of course, yes. If you write the wrong principle on the test, well, the whole point about writing a solution, so the question is if we write the wrong one, but we do the problem correctly, will you count off? If you write an equation you don't use at the beginning of the problem, then that's not really all that helpful, because that means you might have written down a fundamental principle, but you didn't start from it. So in order to do the problem and get the right answer, you probably have to have started from some form of a fundamental principle that's actually going to work. So, I mean, you could write all 3 fundamental principles and then do something completely different. And no, you wouldn't get credit for starting from a fundamental principle because you didn't. But if you are going to try to start from a fundamental principle, write it down. Write one of these equations down. And then show how your work comes after that. Your written out solution is a way of explaining your reasoning. So start from a principle, write it down symbolically, expand out all the terms, put in the numbers you know, identify the unknown, solve, not a big deal.